Hello and welcome to another video. In this video we're going to be going over integer break. So in this problem you have an integer and you want to break it down into the sum of k positive integers where k is greater than or equal to 2 and you want to maximize the product. So return the maximum product. So for like 2, since you can only break it down into 1 and 1, you would break it down to this. Then here for this 10 you want to break it down into 3, 3, and 4 and the product is 36. So there is a math solution to this. It's not super intuitive, and I can just briefly talk about it. Essentially, the optimal way to break down numbers is into 3s and 2s, and then if you have a choice, you want to break it down into more 3s than 2s. So we can go into like a little bit of that, I guess, and kind of like explain it. So let's say we have a number like 16. Essentially, we want to be breaking this down to as many 3s as possible, because that's going to give us the biggest result. So if you do, so essentially you would want to break this down into like 12 and 4, and 12 would be 3, 3, 3, 3, and then you have 4, which is 2 times 2. And this would give you the biggest result. So we can try that actually. So if we just actually, so if we just plug that in, so we have 3 to the 4th, and then we add 4, or multiply by 4, we get 324. And if you just did this in only 2s, you would get 8 2s, right? So we can try that as well. So we have 324 here. So if we try 2 to the 8th, we get 256. And so that's pretty much, like, I don't want to go into the proof of this, but that's essentially the math solutions. You want to break it down to as many 3s as possible. And then when you have the option between 2 and 2 and 3 and 1, you would obviously choose 2 and 2 because that gives you a bigger number. And that's pretty much it, but let's actually go into the normal solution now for this. So the normal solution that 3s and 2s one's a little counterintuitive. So let's go into the normal solution and like what we would do. So let's say we have n equals 10. Essentially what we want to do is we want to basically try every single number because these constraints are pretty small, right? It can only be 58. So we're just going to try every single number. We're going to try to break it down into every single possibility that we can. And so this is going to be like a DP solution. So let's kind of break it down into our DP solution here. So for DP, you need 3 things, right, as always. You need a base case, and you need a recursive case, and you need some kind of state. So I guess maybe let's just, that's fine. We're going to do the state first. So let's do the state first. So for the state, this one's pretty straightforward, but we are going to add an extra trait, and it's not going to actually cost us anything. So for this state, we're going to have just the number that we have. And then we also want to make sure, like, did we actually break it before? So if we have a number, we want to make sure that we broke it before because then we can figure out, like, can we use that number? Right? Like, for example, for 10, can we just say, can we just, like, get that number? Like, can we just use 10? Well, we can if we broke it down already, but we can't just use 10 as our result, right? Now, it turns out this doesn't really matter because, like I said, that optimal 3s and 2s thing, it's never going to be optimal to just use the number, but it will matter for smaller numbers. But let's say you didn't know that, then that would be good to do. So essentially, what you want to make sure is, did I break that number down, right? Because you want to break it into at least 2 things. So we're gonna, for the state, we're gonna have a number, and then we're gonna have just like a Boolean of did we break it or not. So we'll call this broken. And that's all we really need to know. And so for the base case, we are actually just gonna keep breaking it down until the number equals 1. So if the number equals 1, then we are going to, like, what should we return? If the number equals 1, you already broke it down, so then you should just return 1, right? So here we can just return 1 because essentially it's like we're going to be multiplying our number by some DP, and so here we should return 1. So for the recursive case, this one's kind of tricky, and this one's going to have 2 things. So we're going to have a result variable, and we're going to initialize it to 2 different things. So like I said, this is assuming you didn't know that the optimal thing is 3s and 2s. So if the number has been broken already, like let's say we had 20, and we broke it down into, like, we subtracted 10 off of it, and now we're at a 10, and we're doing DP of 10, let's say. Well, now we can just take this number, right? Like, this is fine, because we already broke it down once. So if we broke it down we are going to set our result equal to that number if broken. Otherwise, we're going to set the result to 0 if not. And then we're going to try to maximize it. So like I said, realistically, this will never be the max, but you don't know that. So this would be like, if any one of these was actually a possibility, then you would want to do this. So essentially, you're basically saying, okay, I want to just try to set the default case to just taking the number and that's it, and not breaking it down anymore if it already was broken. And if it wasn't broken, then I'll just set it equal to 0, and then I'll have to at least have one break to maximize it. So that's going to be what we set our result into. And then pretty much we're just going to loop from 1 to n minus 1, right? So essentially we want to break it down into, so essentially we're going to loop from 1 to n minus 1, and we are going to try to break this number down, right? And then if we already broke it before, then this is going to be our starting point. So basically we're going to loop from 1 to n minus 1, and then let's say we try to break it down into some numbers, right? Let's say we have like a number 10, and we try to break it down. So essentially we're going to try to maximize here. We're going to try to break it, we're going to try to maximize whatever I we're on. So we're going to loop from, I equals 1 to n minus 1. We're going to try to maximize I times the dp of n minus I, right? So we're trying to subtract some number, and then we're just trying to maximize that whole product. So essentially, kind of like to show you what that would look like is, let's say we have the number 10. So it's not going to be 1, right? So we're not doing that. And then we're also going to have like a visited hash map as usual. So essentially, we're going to say, okay, so first it's not broken. So we're just going to set our result equal to 0. And then we're just going to try to like break it down into a bunch of different numbers, right? So we're going to try to break it down to 1 and 9. So we're going to say like, okay, what's 1 times dp of 9? Then what's 2 times dp of 8? And so on, right? Because essentially every number you chop off is a valid multiple. Because like, let's say we broke down our 10 into like 3, 3, and 4, let's say. So this is really 10 minus 3, right? Which is 7, minus 3, which is 4, and then finally you return that 4. And so here, this is kind of like what we're doing. We're saying, okay, we're going to chop off some number. Let's call it 3 maybe. So we're going to do 3 times dp of 7, and then dp of 7 will be, the optimal solution here will be 3 times dp of 4, and then finally the dp of 4 will be 4. So then we would have 3 times 3 times 4. And that's kind of what we're essentially doing, is we have to loop from every number from 1 to the end, from 1 to n minus 1. We have to loop from every single number. And essentially we're trying every single number from 1 to n minus 1, and we're just kind of like brute forcing what's our best solution. And the brute force isn't super costly, right? So we're essentially just taking a number, subtracting 1 to the number, literally trying everything with a cache. Is basically what it comes down to. We're literally doing a brute force with a cache, and because we only have 58 numbers, the space complexity and the time complexity won't be that bad, because this is such a small constraint, right? Like our loop can only go 58 times, and then it's like 58 squared or something, which is basically nothing. So that's kind of like how you do this without doing the optimization for 3s and 2s, because that one's not super intuitive, while this one's just like a standard DP problem to ensure that you at least broke down your number into 2. So let's kind of code this up and see what this looks like. So what we're going to do is we're going to have a visited, as always, and we're going to have the number, and we're going to have this broken check. And so our base case is going to be if the number is 1. You can maybe test for like number equals 0, but I think like there's a bunch of ways probably to do this, but this is just what I came up with. So if the number is 1, we're just going to return 1. Obviously, if the number is invisited, we're going to return that as well. And so now we are going to set our result equal to 0. And if it's already broken, we're actually going to set the result equal to the number, because that's going to be like our starting point. Because let's say we have a number like 4. If 4 was already broken from something else, right? If we have a number like 4, if our original number was 8 and we broke off something to get the 4, then 4 is a valid result. Where if our number is 4 and that's just original number, then we actually have to break 4 down one time at least into 2 numbers. So that's why we're just going to set our result equal to the number, because we're going to try to maximize against that, right? So if we can get something better than 4, in this case, if this was 4, then we're going to replace it. But otherwise, we're going to have it there. And so now we just loop through every single number. So for I in range 1 to number, right? So we just need to loop from, so if our number is 4, we need to loop from 1 to 3 to try to subtract 1 to 3. We don't need to subtract 4 because that's already checking for this. If we subtracted 4, our result would just be 4. So we're essentially looping from 1 to that. And also we don't want to do like 0 because we'd get like an infinite loop and all that kind of stuff too. I guess maybe we wouldn't really, yeah, I guess we wouldn't get an infinite loop because we'd end up caching it. So I guess you could maybe change this around where instead of having this broken thing, you could actually loop from 0 to the number. That would probably work. So anyway, yeah, so essentially we're just going to try to maximize our result. And this is going to be I times dp of number minus I. And then now that we broke something off, we're going to set broken equals to true. And then we are going to cache it and return it. Return result. And we're going to do this where we are basically calling it, and then our initial pass into broken will be false. So for example, if you pass in a 4, you don't want to make the result equals to 4. You want to try to break that down into 2 numbers. Similarly, you have to do this, like let's say you pass in the number 2. So the best result for number 2 is not 2, but if you set res equal to the number, then you will actually return 2. So for 2, you actually want to return 1 because you want to break the 2 down into 1 and 1. So that's why you have to have this broken check. Otherwise, yeah, I think otherwise it wouldn't work because you can't, you have to make sure you break at least once. So actually setting this to like 0 and the number wouldn't work because you still have to have some kind of check of like, did I break the number already or not? So I think this is like probably mandatory. And so let's try to run that. Yeah, let's see. And this is kind of all over the place. I think this is like the solution that most people have, I guess. So it's like a medium solution. Like I said, the math one is a lot more efficient, but that one is not intuitive, so I'm not going to go into that one. I personally don't like going into solutions that are not really intuitive for coding interviews that are just going to serve you for like one problem. There's kind of like not much of a point for that. But yeah, you can try to code with the math one if you want, where you're like I said, your optimal scenario is literally just trying to figure out how many 3s do I have. So you can just mod your number by 3s, figure out how many that is, and then figure out like the result and stuff. So you just literally break it down to 3s and 2s. But for this one, our time complexity, not JavaScript. So our time complexity, essentially for every single number, we are looping from 1 to the numbers. This is like an n-squared solution. But because our number is so small, it's fine, because our number is only 58 squared, which is basically nothing. And then our space. So if you think about it, if you think about like what's our worst case recursive stack frames here, it would be just subtracting 1 every time, right? So we'd have like 58, and then 57, 56, and so on, which would be O of n. And then we also have the cache, which would be O of n, because that could hold every single number. So those are both O of n. So we have O of n space, O of n squared time. And yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. So thanks for watching.